So the largest collection of folks, as I mentioned, is the what we call dev tech engineers, developer technology engineers. You could also call them applied research. Other companies sometimes call them applied research. And then physics engineers, I mean, some guys kind of developing the core SDKs and algorithm for physics simulation. And this is a big group of folks. They work for a shoe. They'll develop new graphics features. So they'll develop new physical simulation features, and then they'll help integrate those innovations directly into games. They spend a great deal of time helping developers extract the best performance they can out of any piece of hardware. We'll go through a lot of examples of this, and they don't do that just for NVIDIA, by the way. They just try to improve the game's performance in general. And oftentimes, and actually there's plenty of examples I'll give you where through our work, we've improved ATI's performance at least as much, if not more so, than our own. Right? Because we're just trying to get the frame rate better, because that's better for the end user. It's a better user experience. We'll help teach people CUDA. We'll implement effects in CUDA, or really any computing technology, be it OpenCL or direct compute or CUDA or whatnot. One of the things that's really cool is we firmly believe that physical simulation is one of the kind of new things coming to a lot of games. But with a lot of these physical simulations, there's a really complex, interesting graphics problem to be solved too. So for example, you saw Dark Void, that turbulence effect, with the disintegrator gun where the sparks and stuff fly everywhere. Well, the simulation for that is really complicated, and doing that inside of a game is actually really innovative, because we have a gridded solver that actually kind of migrates and moves through the world and gets integrated. It's not bounded by space. And then the rendering aspect of all that is pretty complicated too, because if you're going to do smoke or anything like that, you actually have to have a good frame rate. And we've had to invent a lot of technology, not just for the physical side, but also for the rendering side for those kinds of things. We have hundreds of effects in the shader library. We publish the source for that. It's right on the developer website. We have extensive programming guides and documentation. We teach classes. We do courses. It's a like I said, it's a big effort to make sure that the industry continues to advance the state of the art. One of the important things that we do, as I said, is learn from developers. Both from their current games, we spend a huge amount of time understanding all the current games and engines and what they do well and what we could do better, but also where they want to go. So we work with developers on things that are 2, 3, 4, 5 years out. They're doing research too. We get a lot of their code in, we'll get models in, we'll get use cases in, and we'll understand what they're really trying to do, and then build the hardware to do that well. So probably the most timely example of that is with DX11 tessellation. We work with Valve, with id, Valve, Bungie, a bunch of folks to get content and understand how they intend to use tessellation, or they might use tessellation, make sure the hardware is good for that. We even build huge simulation infrastructures, tool sets, and prototyped a bunch of things. Wrote hundreds of thousands of lines of code to make sure that it would kick butt. That when we actually built the hardware, not just the hardware, but the software and the API and implementation would work as the developer expects it to work.
By the way, that's a model from Valve, which we used. We worked with them over the last 2.5 years. And we took that's displacement map with subdies and everything. And we actually took their model, worked with them. We created, in this framework, this is rendered on DX10 hardware using our emulator, which emulated DX11 tessellation functionality. It was not as fast, of course, as Furby's GF100, but it still gave us the visuals to tell, oh, this will work, or whether it won't work.
The other thing that we do is NVIDIA actually has a pure research group, and so if the content group is maybe looking out 2, 3, 4, maybe 5 years, the research group sometimes will look out as far as 10 years. And we're constantly trying to take new techniques for graphics or physics or AI and implement them in ways that are beneficial today or very soon for game developers. And so you saw that with ray tracing. Ray tracing is a ways from being useful in a fully immersive way in a game. And yet there's subsets of that we can work with game developers and start implementing right now. Along the way, we're going to learn all sorts of stuff too about, this works, this doesn't, so that as the hardware continues to advance, performance roughly doubles year over year. So while we're running at a few seconds per frame for that kind of quality rendering that you were seeing before, if we're at doubling every year in 8 years, we'd be 256 times faster. At that point, you're going to start seeing something maybe at that image quality. I mean, it seems like it's a long way away, but I've been in NVIDIA for 11 years, and in the 3D effects a few years before that. I mean, 13 years ago when I started in the GPU business, I can still remember it. It doesn't seem that long ago. So 8 years is not that far away, frankly. We hold these developer conferences, and then we present to the world at large, all of our research and findings. And so we had 18 presentations and papers and panels at SIGGRAPH. That's many times more than anyone else in the graphics hardware space. And then recently at i3D 2010, we had 4 presentations, and I don't actually think our competitors had any. So we take this really seriously. We really are trying to enable and teach the world next generation effects and things like that. Yeah, so like I said, we spend a huge amount of effort here. So not only does it impact the hardware, it also impacts the APIs. If we hadn't started as early as we started on tessellation, then DirectX 11 wouldn't be what it is. It would have been much lesser good. We take all of our learnings and all of our understandings, and we try to feed it in to the APIs to make the APIs as good as they can possibly be. Sometimes we do a great job, sometimes we do a lesser good job. We didn't do as good a job on DX10 as we should. The geometry shader implementation, frankly, didn't get as much attention as it should have. Right? So, NVIDIA can take the blame, the industry can take the blame for that, but I think we've done a much better job, for example, with DX11 compute and tessellation and stuff like that. So we started on that years ago, and we're just now starting to see the fruits of that. Tools-wise, I mentioned this before. This slide looks busy because there's a whole bunch of tools that we produce. Things like Nexus, which there's a full presentation in OC right after this one, then we'll go into that. CurveHUD, this is probably the de facto standard for performance and profiling for graphics and games right now. Probably not 100%, but maybe 100% of game developers that are developing a PC use CurveHUD. It is the way you do performance and profiling on the PC. SDK examples, physics tools, SDKs, graphics SDKs, APIs for gathering information about how many cores and what size memory is your GPU, that kind of stuff. Tools for the authoring and production process for shader prototyping and texture compression, and just a huge range of things. Dozens and dozens of tools are produced and that are then integrated into the game developer pipelines. This is an ongoing investment. We've been at this for more than 10 years. And developed a really large body of tools that the game developers are